I have been using R for over 15 years now, both in academic research and for business analytics, and in this video I will show you the most common parametric statistical test that you should know. With examples, I will teach you when to use the test, how to run it in R, and how to interpret the results. Before we dive in, let's zoom out for a second, because most statistical tests fall into one of these three big questions. Are there any differences between groups, for example? Are two things associated? Are they similar? Is there a relationship so that they move together? And can one variable predict another? Almost every test you'll see in this video fits into one of these. So after you watch this video, you will know exactly when to use which test to answer one of these three questions. But the logic between these tests is a bit counterintuitive, so we have to clarify a few terms quickly. All of these tests will start with the null hypothesis, or the assumption that there is actually no difference, no effect, no relationship, only noise or variance. And then the p-value will give us the probability of seeing data or results at least as extreme as ours if the null hypothesis were actually true. And if this value is very low, we say that it is pretty unlikely that the null hypothesis is true and we reject it and accept an alternative or the research hypothesis. Rejecting the null comes with a risk. We might be wrong and then we commit a type 1 error. We reject the null hypothesis when it is actually true, and then we claim that our discovery is real when it actually is not. And this will happen in 1 in 20 cases. That's your crash course on hypothesis testing. Let's kick things off with our first test, the t-test, which comes in a variety of one sample, two sample, or paired. We will use it to find mean differences between groups, and we will use the var test to check for equal variance, and I will tell you when to use the more powerful paired version of the test. Each version runs with the t-test function in R, and you can use the question mark or the help function for all of these tests that we're about to see today to get additional information, to see what function arguments exist there and what the default setting is. So for the t-test, it assumes not equal variance and not paired groups. Then it comes with explanation of the function arguments as well as the output parameters you get from running the test, and then you always have some examples at the end. Let's look at the one sample t-test. Imagine we have 100 patients and their average blood pressure is 140. So BP is blood pressure, and I created a random normal distribution for a mean of 140 with a standard deviation of 10. So here I created 100 patients with some variance around these parameters. And now we can run the t-test for one sample and the blood pressure variable and ask if the average of 140 is significantly different from mu, a value that I set to 120, which I would consider the normal blood pressure, and the p-value comes down to e to the power of -16, so very close to 0. It gives you the alternative hypothesis that the true mean from our sample is not equal to 120. That is what we were testing. You get a 95% confidence interval of the estimate, which, giving the sample size of 100, ranges from 138 to 142, and the mean sample is estimated as almost 140, which is what we simulated. So yes, our group blood pressure is statistically significantly higher than 120. Such a big difference is very unlikely to appear from a population with 120 blood pressure. It's always a good idea to visualize your distribution or your sample. Here with a simple genome histogram, you could add the density distribution in orange, so you see it looks pretty normal, and we can add a vertical line at the position 120 to show that this is the mu we want to test against and ask if our distribution and its average is different enough from this 120, which our t-test claimed it was. Now for the two sample t-test, I split our 100 individuals into two samples, A and B, just by filtering the ID to the first 50 and then the last 50, and I just subtract 10 from the second sample. So we can imagine they followed some treatment or took some drug to lower their blood pressure, and on average they lowered it by 10 points. Now you get the average estimate, so just the mean of sample A, it's 141.5, and sample B is roughly 10 points lower, 128.4. The p-value is again close to 0, so definitely below 0.05, which means that the t-test tells us that these two samples are statistically significantly different from one another, and the estimated difference is between 9 and 17. That's the confidence interval. Here I specified the x and the y value. You can also use the formula format. For this you need a data frame with a group variable. So now in group you have A and B for the first 50 and then the next 50 individuals. And then you can run a t-test where you want to see whether the variable blood pressure is different for the group levels, and the data is our data frame. So same result, just different format, not x and y, but this formula expression. We can plot our different groups here with a box plot to see that the average are different. You can also use the density plot to see that there's still some overlap, but A and B are different enough for the t-test to pick it up. As we saw with the help function, the variance is not assumed to be equal by default. We can set it to equal, and then you see that the p-value decreases slightly. So the default assumption is a bit more conservative. And how do we know that the variance between the groups is actually different or the same? We can use the var test that starts with the null hypothesis that the variance is the same, so that there's no difference. And in this case, the p-value is 0.9, which means that our data does not allow us to reject the null hypothesis and claim that the variance is different. You can also see that here that the 95% confidence interval includes 1, which is the ratio of variance, and 1 means equal. Another thing you could do to improve the power of your test and reduce the p-value is if you start with an assumption that one group is greater or less than the other. By default, the t-test is two-sided, so it's open to either one of the groups being less or greater than the other. But if you assume that the treatment reduces the blood pressure in group B, so group A has a greater value, you can say that in your t-test, and then the p-value gets smaller than we had before. It's exactly cut in half, and now the confidence interval goes to infinity. So it's not 10 to 17 as before, but now we know it must be greater, so it could be infinitely greater. For the paired t-test, I created two groups with only 25 individuals and a slightly higher standard deviation, and the second group has a reduced blood pressure of 5 and then some error attached to it. So now reduced sample size and reduced effect difference. As you can see in the box plot, the median is lower, but there's a lot of overlap. As you can see with the density plot, the second group is shifted to the left, but not much, not as big of a difference as we had before. And now the t-test for this sample would not be lower than 0.05, and we could not claim, based on our small sample size, that this intervention, like some drug that reduced the blood pressure by -5, was effective, because there's such big variance between the groups. But what if I told you that there are not two groups with 25 individuals, but there is only one group of 25, and it gets measured twice, before taking the drug and after. So each individual is paired with two values. The blood pressure 26 belongs to the same individual with the blood pressure 1 just after the intervention. And now the t-test is a paired t-test, and it's highly significant. And that comes from the fact that each individual has a paired value from group A pre-test to B post-intervention. And if we color the lines based on whether they increased or decreased, we see that most individuals, this -5 blood pressure reduction worked. With the variance I introduced with the arrow, you see that sometimes the line goes up, but only in 9 out of 25 cases. So the t-test asks whether this distribution of change is significantly different from 0. And since most values decreased, it can reject the null hypothesis that there is no difference. If you ever want to extract values from a statistical test, you can store it like in a results object, and then the str or structure function tells you that this test is a list of 10 entries, and you can specifically extract values from that list. So results $p.value gives you the p-value. So as I said, the paired t-test compares not two distributions to one another, but is interested in the change, and then asks whether the average of this change is different enough from 0. So these are all of the 25 individuals where we subtract the pre-values from the post-values. We can plot them in a histogram, and then ask if they are different from 0 with a t-test. So this would now be a one sample t-test again with the change values compared to 0, and this gives us the exact same p-value as did the paired t-test. It says that the average of -4.6 is unlikely to happen with a true mean of 0, and then it gives us a confidence interval of change, which is the exact same confidence interval that we had from the paired t-test. Now what do we do if we have more than two groups we want to compare? We can use the ANOVA, or analysis of variance, that compares the variance between groups to the variance within groups, and then runs the f-test or the f-statistic. We will follow it up by pairwise comparisons that we do with the Tukey function, and then we have several tests to check if the variance is equal. Let's say you're comparing the IMDb rating of all seasons of a TV show and you want to know if there's a season that stands out, good or bad. And here I have the data of the 9 seasons of How I Met Your Mother and the individual ratings of each episode within the season. And now the ANOVA asks whether one of these groups is different from the rest. Might be season 2 being better than the rest or season 9 being worse. This is not what the ANOVA will give you. The ANOVA will not tell you which season it is, but just if they are all the same on average or if one or more stand out. Here I have season 2 in green and season 9 in red and the different episode distributions, and in black is all seasons ratings. And you might want to use the t-test to compare season 9 to season 2, and this could come out significant, but if you test 9 seasons in all the different pairs to one another, you would do so many t-tests that you inflate the type 1 error rate, and that's where the ANOVA comes in, and we just do one test to find out if there's even anything there, any real effect we should further investigate. You could also use histogram and facet rep to show all other seasons compared to season 2, which seemed to be the best, and season 9, which had many of the lowest rated episodes. If you just run the ANOVA function, predicting rating versus season, and the data is our How I Met Your Mother dataset, which simply holds the season number, episode, title, and then the rating, and how many votes went into these ratings. So running the AOV or ANOVA function by itself is not that informative, but we can use the summary function wrapped around that expression to get the p-value and the f ratio, which is the ratio of the mean square. 1.45 divided by 0.3 is 4.8, and this is the variance between the groups, the seasons, and the variance within each season, so the residuals that remain. Each have a degree of freedom, 200 episodes -1 and 9 season -1, and then you divide this by this to get this, and this by this to get this, and the ratio of it is the F statistic, which in this case is highly significant. And we could claim that the seasons do not come all from the same distribution of ratings, but there is some group effect going on. And to find out more about this group effect, we run the Tukey HSD function, which stands for Tukey honest significance differences, and it has a correction for pairwise comparisons to not inflate the p-values. It gives you the adjusted p-value of each comparison from each season. And we can find the pairs of highest difference and most significant p-values with some data manipulations. And here we have them sorted by increasing p-value, and only the first 8 rows are significant. This is 0.03 and this is 0.4. So season 9 compared to all other seasons is significantly worse, and then season 2 is also better than season 8. But the main effect comes from season 9 being the worst, which is interesting because season 9 had some of the worst rated episodes, but also overall the best rated one. And here you can see that the last 2 episodes were actually part 1 and 2, very low rated. And I will have a dedicated video where I go into more details of ANOVA, comparing the endings of several TV shows. You can also plot these differences and then see left of 0.05. These are the pairwise comparisons with adjusted p-value that's significant, and the rest is pretty equal. Now when you look at this, you might suspect that the variance is not equal throughout these seasons, which is an assumption that has to hold true. For the ANOVA to work, there is a test called Bartlett test for homogeneity of variances. And when this is significant, it means that we have to reject the null hypothesis of the variances being equal. And this is entirely caused by season 9. If we exclude season 9, then this test is not significant anymore. And we could run the ANOVA on season 1 to 8, which I did, and there season 2 came out to be significantly better than the rest. We can also run the Levene test. That's a bit more robust and conservative, and this also comes out significant, meaning that the variance is not equal across the groups. And we see that when we group by and summarize, here season 9 has a much higher standard deviation and a higher variance. Nonetheless, when we do a t-test comparing season 2 and 9 with variance equals being false, it still comes out significant. Based on 46 episodes, the rating difference is big enough to claim that those are significantly different. And in my dedicated video about ANOVA, I tell you how you can deal with unequal variance. Next, I want to cover a two-way ANOVA. We have tooth growth data with the length of t's, 60 different samples, and now we have two factors that go into the prediction of tooth length. One is the supplement, being orange juice or vitamin C, so 2 levels, and the other one is the dosage, so small dose, medium dose or high dose, and for each of the groups we have a sample size of 10. This is the formula to run the ANOVA based on 2 factors. Now with interactions, this would be without interaction if you use the plus sign. With a star it's the interaction term, and we get a summary where the dosage is significant, the supplement type, and the interaction. And a way to visualize interaction in linear models or ANOVAs is with a line chart, where you can see that orange juice is more effective than vitamin C for tooth length. That's why the supplement type is significant. You can also see that overall the dosage increases tooth length. That's why that's significant. But the interaction happens when the effect of supplement changes as the dosage changes. So these slopes here in parallel now collapse into a single value, which means that the slope for vitamin C is steeper than for orange juice. Enough with the differences. Now we want to look at relationships, and we start with the correlation using different functions to ask whether two variables go up or down together. We can start with a very easy example of 15 women, where we have the height in inches and the weight in pounds converted to centimeters and kilogram. We can use the corr.test to ask whether women height and women weight correlates, and we get almost perfect correlation. Correlation coefficient can be between -1 and 1 for perfect correlation, positive or negative, or 0 for no correlation, and this is highly significant. If you just use corr without the test, you get the correlation coefficient, but not the test statistics and p-value. There's a function from the psych package called cor.test, but with double R, and this allows you to run correlations for multiple variables at a time. So the famous iris dataset has 4 measurements: sepal length and width, and pedal length and width, and here you would get correlation values and the p-values. So these are almost all significant except for one correlation pair. If you just look at this object, you get information to run the print function with short equals false to see confidence intervals of the correlation. So then you get this extra table with the raw p-value and the correlation, and upper and lower confidence intervals of the correlation coefficient. However, there's an important problem to mention here with these correlation coefficients, something that you might know from the Simpsons paradox. The correlation value of a whole group can be misleading when you look at the individual correlations within the groups. For example, this scatter plot has a negative correlation, so a line would go from the top left to the bottom right, in this case not significant. But pedal length and sepal width, this chart here, has a moderate negative correlation that's highly significant, and it looks like for these two variables there's a negative correlation. But when you add color to these charts to emphasize the groups, this negative correlation of -0.4 completely breaks down, and now you see that it's actually a positive correlation within each species. So these are 3 different species of iris flowers, and for setosa these two variables don't correlate significantly. And here between sepal width and sepal length, that's this chart, we had a negative trend going through the scatter plot, but for all 3 species it's actually a highly significant and strong correlation. That's why it's important to always plot your data to find these effects. Pedal width and pedal length is one of the rare cases where the overall correlation is in the same direction as the within species correlation, but only for one species it's actually really strong. For the others it's more of a scattered cloud than a clear correlation trend. And I have 2 more videos that I link here that emphasize the importance of visualizing your data. One of them is about the famous Anscombe quartet, where you have 4 different data sets that all have the same mean of x, y, the same correlation coefficient, the same variance, standard deviation, and linear model variance explained, but look completely different. Another thing that's worth saying is that correlation is not causation, especially when time is involved. Some things just change over the decades. For example, the distance between Neptune and the Sun almost perfectly correlates with the burglary rates in the US, and you can find these spurious correlations on tylerweigen.com. And the last thing on correlation, Here, for example, with the sine wave, the y value is almost perfectly predicted by the x value. Still, the correlation is 0 and corr.test is not significant because these values do not go up or down together. So as x increases, y sometimes goes up, sometimes goes down, and it's meaning that they don't linearly correlate. But prediction brings us to the next statistical test or procedure I want to discuss, which is linear models, single or multiple linear regression, and how you can predict one value based on other variables. We will talk about the p-values of the different coefficients that we are trying to estimate, the intercept and the slope, and as a bonus I show you a quick way to get the regression results into a nice publication-ready table. Here I started an example linear model data frame with 11 values for model 1 and 11 values for model 2, and when I plot them, would you be able to tell me which model has a stronger correlation? Model 1 definitely has a steeper slope. If I set the standard error to true, you would get these narrow or wider confidence interval to estimate the mean of these scatter plots. But when you run the correlation tests, you see that model 1 and model 2 both have almost identical correlation coefficients, both significant and identical, even though it looks like the y and x values here are more tightly correlated, because here the slope is steeper. It allows for more variation on the y-axis to still create the same correlation. So as you can clearly see, the deviation from the average slope is higher in model 1, but because the y values increase faster with x, this increased variation is allowed and you still get the same correlation coefficients. However, the estimates are clearly different. In model 1, the slope increases with 4.4 with every x, and in model 2, the slope was much narrower, only 1.15. And this is the big difference between linear models and correlation tests. The correlation can be the same and the variance explained that we have in R square can be the same, but with linear models the effect of the coefficient matters. If you want to predict one value based on x, it matters what y value you get, and this you get from the slope. So model 1 is clearly different from model 2 regardless of the identical correlation terms. You can see that in the second example. Here now the slope are identical, but the arrow that I generated is much bigger for model 1, which then of course would lead to different correlation coefficients. With the dollar estimate, we can extract the correlation coefficient from the corr.test, and when you have identical slope, then the less variation you have around this regression line, the higher your correlation will be. For model 1 it resembles more of a cloud. Let's predict something real. The empty cars dataset has cars from 1974, and we can try to predict the mileage, so the miles per gallon, based on the weight of the cars. The weight is in 1,000 pounds, and you can see that the heavier the car is, the less mileage you get from a gallon of gas. When you use the plot function, it asks you to hit return to see next plot, and then it gives you a distribution of residuals versus fit, and also the QQ residuals. They should all be on the same line, but there are values above at both tail ends, which indicates that a linear fit might not be the best. And when we take out the method being linear model from the geom smooth function, you see that it rather wants to fit in curve, where it goes down steeper in the beginning and then fades off as the weight increases. The mileage is less and less influenced by it. When we run the linear model predicting mileage based on weight from the empty cars dataset, we get two estimates, an intercept and a weight. Negative term here, both are significant, and the intercept means that if you have zero weight, so a car that doesn't weigh anything, you would get a mileage of 37 miles per gallon, and then with every unit of weight you go from 2 to 3 or 3 to 4. This mileage is reduced by the factor of 5.3. This is how the blue line is created. At 0 you cut 37, so that would be around here, and then with 1 and 2 you go down and down. Both terms are significant. This is the p-value, and the adjusted R square tells you that 74% of the variance is explained by one factor alone, by the weight variable, and the overall linear model is significant. When you ask for the correlation between these two variables, mileage and weight, this is the correlation term, minus 0.87, strong negative correlation, and R squared comes from the fact that when you multiply the correlation coefficient R with itself, you get R squared, and this is the 0.75 that you see here, multiple R square. and the adjustment reduces it a little by taking the degrees of freedom into consideration. And when you use structure on the summary, you get a list of 11 variables where you could extract the adjusted R-square directly, or the intercept, the different coefficients like intercept and slope. So here, with this line of code, you get the R-square value directly in case you need it. Now, can we improve this model by including more variables? As you can see in the plot, the cylinders of the engines show different slopes. And if you include this factor, the variance you explain with this more advanced model already increases to 82%. If you include the interaction between weight and cylinders, you could even increase this to 83%, but then it gets a bit tricky to explain. Here you can see what we showed before. As the cylinder changes, the slope changes, which represents the interaction between these two variables. And just so that you know these options exist, there's the GT package that allows you to create publication-ready tables of your linear regression results. Here's the code for that. There is also a package called GT Summary that makes the whole process even faster. So here you get a nice table with the intercept and then the estimates and confidence intervals and significance scores of the different estimators and the interaction effects. And the whole reason we do linear models is to predict Y based on X, or mileage based on several variables. And when we have this model, we can create new data. For example, with expand.grid, we now have a new data frame with different weights, 2, 3, and 4, repeating for the different cylinders. And then we can use the predict function on our model that we created above with the new data. And when we view that, we see the different estimates of mileage. So 4 cylinders at a weight of 2 has 28 mileage. That's simply the Y value on the red line. When we predict 3 for 4 cylinders, we get 22.6, so that's around here. And just to clarify, this simple model where we predict miles per gallon by weight fits a straight line with a slope and an intercept, and it explained 74% of the variance. The advanced model that now takes cylinders into consideration still only gives you one intercept and one slope. So this chart is a bit misleading because here you get the perfect fit per group. So 3 different linear models with 3 different intercepts and slopes. And therefore I added a line with the model's intercept and slope, so just one slope that goes through all of these points. And the best fit is created because it adds an additional punishment, fewer mileage, for 6-cylinder cars and 8-cylinder cars. This is what's called dummy coding. Without this adjustment, you pretend to be a 4-cylinder car, but then for this new factor cylinders, which does not go in as continuous variable 4, 6, 8, but dedicated levels of a factor. All of these are significant, and the punishment for 8 cylinders is just a subtraction. It behaves like the intercept. You just lose 6 miles per gallon by default if you're an 8-cylinder car. So this black line is slope and intercept of the more advanced model that now explains 82% of the variance. And that is also how the predictions were created. Knowing the weight and the cylinders, it went by the intercept value and then subtracted 2, 3, or 4 times the slope component multiplied by this value. And if you're 6 or 8 cylinders, there's an extra punishment going in regardless of your weight. So if we want to predict the mileage for a car with a weight of 4 and 8 cylinders, we start by the intercept, add the weight times the slope for the weight, and then we add the dummy coded cylinder 8 punishment, and then we get 15.10, which is similar to what we predicted here, plus minus the rounding errors. But what can you do if you don't want to predict a continuous variable, but a binary one, like an outcome of success or failure, a 0 or 1, a yes or a no? That's where you go to Logistic Regression, which is a generalized linear model where we pick a certain distribution to link our input and output variables with. And it can get complicated to understand the log odds and how they relate to the linear model. You won't get an R-square, but there are ways to get approximations of R-square. And as an example, I'm using a diabetes dataset where we have multiple continuous variables and 768 observations of people from India that are either diabetes positive or negative. We have the body mass index, blood pressure, glucose levels, number of pregnancies, and age. With the with-miss function, we see that insulin and triceps values are often missing. We will exclude those as predictors for the logistic regression. And for the future code, I'll just turn the original dataset into this new object called diabetes. And for the basic model, I just want to predict diabetes based on body mass index. We can create a data frame that predicts the probability of diabetes based on this model. Now we use GLM instead of LM, and we need a family function argument to specify that we want to do logistic regression. The summary function gives us p-values again, so it seems that the BMI is able to predict probability of diabetes to some extent. This S-shaped curve is typical for logistic regression, where your probability of diabetes is either 0 or 1. So these are all the different individuals, and you can see that for people without diabetes, the range of body mass index is roughly between 20 and 40, and it's slightly shifted to the right for people with diabetes. And this blue line is the fit, the predicted probability, where, for example, at 38, 39 BMI, it becomes more likely that you have diabetes. That doesn't mean that you cannot have diabetes with 30 or 35. It's just the best fit through all of the data. How can we interpret these estimates? As I said, it gives you the log odds, and the mathematical conversion of log is exponentiation. When we use this logistic regression model to predict new data, like the likelihood of having diabetes at a BMI of 32, whenever we get a negative value, it means that we are below 50%. And if you put in this new value into our estimates, you get a negative value, which means by default you don't have diabetes, but with every increase of 1 BMI, your risk of diabetes goes up. Important to know that the log odds behave linearly, whereas the probability does not behave linearly. And when we get the odds from our log odds with the exponential function, we can turn it into a probability with this formula, and this is the likelihood of not having diabetes. So at 32 you are here BMI wise, and 1 minus the last value that we did in the console means you have 32.8% probability of having diabetes at BMI 32. And there is already a p-logis function that works directly with the output of our model, and it comes down to 32.8%. Also the predict function we can use with the link from the model, but we can already turn that into the response, and then it also comes out directly at 32.8. One more example, what happens if we now go up 1 BMI? We had 32.8% probability. Now we predict and get a slightly increased value. It's increased exactly by 0.1025. We can turn that into odds again, or directly use the p-logis function, or predict it, and that means going from 32 to 33 and having these probabilities is an increase of 7%. But going from 42 to 43, another 1 point increase, is now only a 4% change. So that's the important difference between probability and log odds. The log odds go up linearly with each point of BMI, but going from 32 to 33 is a steeper increase than going from 42 to 43. That's why this shape is not linear and probability behaves different. At some point, going from 60 to 61 doesn't change your risk of diabetes much because you're already above 80-90%. As you saw, the model summary does not give you an R² of how well the model does, but there's a way around that. With the PSCL package, you get values like McFadden or R² maximum likelihood estimates that resemble the variance explained part by our logistic regression model, and it says that BMI roughly explains 8 to 10% of the variance. If we include more variables like glucose level, which is highly linked to diabetes, but also age and pregnancy and pedigree, estimates from family history of diabetes, you see that most of these variables have predictive power. You start with a lower intercept, but now all of these starting to add up your risk of diabetes as they increase, and the p-r² function of this Fuller model now jumps up to explaining 28 to 30% of the variance. Let's talk about proportion tests next. They are essential when you're comparing things like conversion rates of websites or success rates or death rates in general across groups. The prop test needs a vector of x and n, which represents number of success and n is the number of trials. And in one of my recent videos I investigated the mortality rate of 2 different clinics in 1840s Vienna, hospitals where women would come in to give gave birth, but then died of an infection, in some years between 7 and 16% of the time in clinic 1, but only 2 to 8% of the time in clinic 2. So we have two different proportions, and we can use the prop test to compare them. We have two vectors. One holds the number of deaths from clinic 1 and 2, and the other one is the n vector that holds the number of trials. And the prop test gives you a very significant p-value, also because we have a really high sample size over 6 years. It gives you the summary proportion, 10% in clinic 1, 3.9% in clinic 2, and it estimates a 95% confidence interval of the difference, so between 10 and 4%, that's 6, with 95% certainty that it lies between 5.5 and 6.5%. For the proportion test, you can use two vectors or a matrix. So here we have a matrix of death and birth, and you can feed that into the prop test. However, you have to be really careful, because if you just use the same matrix as the table we had before, you get different estimates. So now the proportions are different, 9 and 3.7 instead of 10 and 3.8, and also the estimate of the difference changed, because the matrix does not want the number of success and trials, which gives us these correct proportions, but what the matrix wants is the number of different outcomes. It wants to know the ratio between death and survival. So this row adds up to 20,000 trials, and in clinic 2 this adds up to 17,791. That's total number of n, but if you use a matrix in these proportion tests, it wants to compare success versus failure, or here death versus survival, which means now with this updated matrix we get the exact same values as before. Something to keep in mind. Within the proportion test you can also specify the alternative. So if you think that clinic 1 does something worse than clinic 2, you expect the proportion to be greater in clinic 1, and what happens then is your p-value becomes smaller, you have more power, but also the confidence interval now goes to 100%. So for a proper estimate of the confidence interval, I always would go with the alternative two-sided. As you can see here, alternative two-sided is by default, and then you get a good estimate of the proportion difference of your two groups. Speaking of confidence intervals of a proportion, the binom.test creates one for one sample. So imagine you run an ad on a website 100 times and you measure your conversion rate. You get 20 clicks or sales based on 100 trials. It estimates the real conversion rate to be between 12.6 and 29%, so rather wide, but that's because you have a small sample size. And if someone says, if you run the ads here, we guarantee a 30% conversion rate, you can check your sample against that. It would come out significant, saying that it's probably not 30%, because your 95% confidence interval of this proportion is below the 0.3 that you gave it. Instead of the binom test, you could also just run the prop test on one value. You get the same estimate. Notice that the higher the sample size, the more narrow it becomes, and then you can compare the two proportions to one another to see if the sample 2 with 16% conversion rate based on 500 ads you run is different. And here would come out as no, so be aware, small differences only become significant when you have a really high sample size. Here the estimated difference includes 0, which means you cannot reject the null hypothesis that there is no difference. So in order to really differentiate a 20 to a 16% conversion rate, you need almost 1,000 tries to become a significant statistical test. And here you can see that it runs these tests by default with a continuity correction. And this continuity correction you only need for really small sample sizes. So when you get into the realm of 1,000, you can set this to false, and then it's without correction, and your p-value becomes smaller immediately. The chi-square test allows us to see whether two categorical variables are independent from one another, or whether the different levels of them appear randomly. If they are independent from one another, then the frequency at which they appear together would correspond to the probability of them existing all by themselves multiplied by one another. And for this example, we use the tables with different hair and eye colors. We have 592 observations of them appearing together for males and females. We can combine them into one big table, and it's not really easy to see whether brown hair and brown eye appear more often than one would expect. The add margin functions adds the row sum and the column sum to a table. We still have our 592 individuals, and the probability of having blonde hair is 21%. Blue eyes in our sample is 36%, and if hair and eye is independent from one another, then the joint probability of blue eyes and blonde hair is 7.6%, which means in a sample of 592, we would expect 44.7 individuals having this combination, but we have more than twice as many, which indicates that there must be some relationship and that these two variables are not independent, and the chi-square test looks into that exactly, and for our table it comes out as highly significant, and we could reject the hypothesis of being independent. When we save the results of the chi-square test in this test object, we can extract the observed observations and also the expected ones. So what we just did for blue eyes and blonde hair, the test automatically does with some rounding errors exactly what we calculated by hand. We can create a table that calculates the standardized residuals for each combination, which is the number of observed values minus expected divided by the square root of expected. It's a way of showing how many standard deviations a combination is over or underrepresented. So blonde hair with brown eyes, very unlikely, but some combinations like brown hair and brown eyes, not that much higher. We can turn that into a heat map that plots the standardized residuals for hair and eye color, and now it's much easier to find the big deviations. Black hair and brown eyes go together much more often, same for blonde hair and blue eye, and it's really hard to find blue eyes with black hair or brown or red hair, but that doesn't mean that there aren't any exceptions. As we saw in our observed table, each of these combinations exists, just not as often as one would expect if the variables were independent from one another. If you don't want to plot the residuals, you can also just do a simple ratio of observed divided by expected, which then gives you the percentage increase. So now I have a plot that shows that our observed data of blonde and blue eyes was twice as often as one would expect, a little bit more than twice. We saw that here, that we had 94 in our sample, even though it should have been just 46. Red hair and brown eyes is exactly as often as expected, but hazel eyes with blonde hair, only 50%. Same for blue and black. I find that a bit easier to communicate compared to the standardized residuals. If you have a very small sample size, so few observations, the chi-square test might not come out significant, but the Fisher exact test for count data does, because it is using the exact test for independence, and the chi-square test adds a Yates continuity correction, and only if you set that to false you would get a significant p-value, but it tells you that the approximation may be incorrect because the sample size is rather small. So if this matrix represents a drug versus a placebo and you want to see if someone recovers or does not recover and the sample size is really small, you should use it to run the Fisher's exact test. To check if a distribution behaves normally, we can use the Shapiro test, which performs the Shapiro-Wilk test of normality. The KS test is more general to compare two sample distributions to one another to see if they are the same or different. And there is a special version of the Shapiro test with an underline instead of a dot. And this test gives you the p-value of 4 different variables in one go. And as you can see here, for the first 3 variables, the p-value is significant and it would reject the distribution being normal. Only sepal width comes out normally distributed, which is weird for a biological measurement, but it can be explained because we know that the iris dataset includes 3 different species, so only the sepal width values are combined in a way that it still resembles a normal distribution, but actually if we would check each species individually, they would most likely behave normally. Let's give that a check. So now for Setosa, only 1 variable is not normally distributed, but the other 3 are. Same for versicolor, the width behaves not normal again, that is the pedal width, and for Virginica also. So 3 out of 4 variables we would not reject the test of normal distribution, and for Virginica all of the 4 look normal. So pedal width is this distribution, and yeah, you can see it's wider and more shaky than the others that approach a normal distribution quite well. And you can plot this only looking at the pedal width, or use the Shapiro test specifically for pedal width after grouping by species. You can see then the rejection of the null hypothesis twice for 2 species. Only for Virginica it kind of looks normal still, but it's close, and the others don't show a normal distribution. I hope you found this video helpful. Let me know in the comments which of these tests you knew already and which of them you use in in your analysis? Do you want to have more of these tutorials, more examples, other tests, maybe some non-parametric ones? If you found this video helpful, please leave a like, subscribe to the channel, come to my free school community to learn more about data analysis, and hopefully see you in the next video. Until then, bye bye here from the Data Digest.